Thanks everyone for coming today. As Brennan said, my name is David Erickson. I'm a PhD candidate in Nick McEwen's research group at Stanford, and I'm the author of the Beacon OpenFlow controller. So I thought to get started, a good way to get you familiar with this is just to do a demo of the controller itself. Today, we have some files available on DVDs later on for the hands-on section if you want to play around with the controller itself. I'm going to give a demo using exactly that package to show you what you can do with it. So I've taken the file from my platform and I've extracted it into this folder here. And the only prerequisite is that you need to install Java on your machine. So I'm going to go into Eclipse here. I'm going to fire up Eclipse, which is our development environment for Beacon. And then I'm going to go ahead and import the code. I'm going to point it to the source subfolder to inside that archive that we distribute. And then I need to set a local target, which just provides libraries for it to build with. And that's it. So we have a development environment up and running. You're ready to run the controller. So we're going to go ahead and do that. We'll go up here to debug. We're going to start with just the hub module of Beacon. Very simple. Fire it up. You can see down here in the console, we're getting some action. The controller is now listening. You can see right there. So I also have a Mininet virtual machine on this box that I'm SSH'd into. This is Windows. Beacon runs in all the common OSs, Windows, Mac OS, Linux, whatever you've got here today, it should run in. So I'm going to go ahead and connect a switch and a couple of hosts up to this running controller. Saw there was some action down here in the console, so we now have a switch connected. Let's ping between those hosts just to verify it works. And we're now getting some ping. So the way the hub module works is a packet comes into the switch. There is nothing in the flow table, so it bounces up to the controller. The hub module is super simple. It just floods it back out all ports on that switch except the incoming port. So you'll see there's a couple millisecond round trip time as this bounces back to the controller. Now let's say there was some kind of problem in this hub module and I wanted to debug it. Let's find this code here. So here's the code for hub. We're going to come down to the receive method where stuff actually happens. And as you saw, we've got a running ping. So why don't we go ahead and set a breakpoint and see what we can find out from that. So Eclipse has now suspended the thread at this breakpoint in the controller. I can step through this code line by line. I can come up here and inspect variables to see what's happening. I can look at that packet in, see why it came in. Oh, there was no match, etc. So you have a very simple development environment which will get you productive and able to debug really quickly. So we'll go ahead and restart that thread. Now, Beacon also has a web interface that comes with it by stock. So let's take a look at this. It's fully extensible, so if you wanted to create a kind of bundle and stack a web interface with that, you can easily add it onto here. We can see it shows that we have one switch connected. So let's look at the flow table. There should be nothing in there because it's running hub right now, which is correct. We'll turn auto refresh on that and come back later. And we can check the port stats just to verify they're working. So we should see an increase in here in just a second as the hub module continues to send packets, and there it went. So I'm going to show you an advanced feature. I wanted to enable runtime modularity of this controller. So what I'm going to do is I'm going to actually stop the hub module. I'm going to start a new learning switch module. Imagine, for instance, that you have a controller running somewhere and you need to either in place swap some code or you want to add some new functionality. We can do this without turning off the controller at all. So if you look right here at the time that the switch connected, you can keep me honest here, we can verify this doesn't change. So I'm going to come here to the OSGI tab. I'm going to find hub, just right here. We're going to stop it. We can make sure pings shouldn't be flowing now. They're not. They've stopped at sequence number 158. So let's install learning switch to this running controller. So earlier I built this learning switch jar file. We're going to go ahead and upload that. It's now been installed. Now shows up in the list, and we're going to start it. And let's see if pings are now flowing. That's good news. Let's check and see. Learning switch should now be installing flows because it knows where the hosts are at. It's more advanced than hub. So sure enough, we now have flows that are showing up in the table. Sorry for the width here. It doesn't work particularly good at 1024. Port count's going up, and let's check if the switch reconnected. That's still the same time. We'll refresh it just to make sure. So the switch didn't disconnect. So I showed you a controller that is running. We've swapped out code at runtime that's in the fast path of packets going through the controller itself. And this is fully dynamic. And you can do this for your bundles. You can replace code, stop it, whatever you need to do. Okay, so I'm going to talk briefly here about motivation, so why I decided to write Beacon in the first place, talk a little bit about design space, and then I'll talk in some detail about what you just saw and how things actually work underneath the covers. So I have to take you back to the beginning, which is like the 2008-2009 timeframe. At that time, the controller world was Knox. And as Murphy gave a great talk about it, at the time, it was a cooperative single I/O thread-based controller that had some glue code to allow Python to run as well. And I should be very clear here, Knox enabled us to do fantastic research for years, and it continues to do so. A big thank you to Nicira as well as the current maintainers of Knox. They've done an absolutely wonderful job. When I was working with Knox, I should say these are just sort of my opinion and observation based of some challenges that I ran into while working with it, which motivated me to try a different path. In our early demos, we used this Python path within Knox. And you could do some really cool stuff with less than 1,000 lines of code. But when we got bigger demos and stuff like that, we started running into some sort of Python-related issues where we would have less exercised code paths, primarily dealing with these kind of weird events happening. And they would frequently have type errors or sort of like syntax errors that didn't occur when we first started the controller. And so these became difficult to debug. We also had problems with Swig. It was hard to export functionality from C to Python that may have been missing or that we wrote. As has been said, it was much slower than C++. So after sort of the initial run of demos, I went off and started doing my own research, and I figured, oh, I'll just build on C++. I'll get rid of having to deal with the Python problems. And this solved most of those problems, although you have the inherent challenges when dealing with C++, like some really hard to debug compilation issues relating to STL templates, boost, you name it. And then you have like the sort of whole class of memory related challenges. And the bottom line is I felt like I was spending a lot of time sort of dealing with these platform issues and not creating the features as a researcher that I wanted to on top. And so I wondered what I could do to try and make a platform where I was able to accomplish this. So I wondered, is it possible to build a controller that had rapid or no compilation time and that could actually give meaningful errors and warnings? I wondered if you could reduce the scope of runtime errors by using a language that had sort of managed memory, as well as some static type checking to remove those types of errors. I also wanted to improve developer productivity, mine in particular. I wanted to ensure that whatever I picked had a mature tool chain and development environment. I wasn't really keen on some of the cutting edge languages at the time. And to me, code generation autocomplete is really important, so I don't have to keep in my memory cache all of the methods that I could possibly need to use in my objects. I also desired cross-platform. This wasn't super critical, but if I'm building from scratch, I might as well try to get it. And I wanted some performance. I wanted to be, give or take within 50% of Nox, or pick a fast C++ implementation. And as I was putting this together, the obvious thing is that most of these are actually language related and not Nox as an architecture related whatsoever. So a candidate language I took a look at is Java. I had a background in Java, so I'm slightly biased here. Some people may say I'm extremely biased. That's probably fair. But there were a couple problems with this. There were no existing protocol bindings to Java. OpenFlow itself is sort of still to date distributed kind of as an openflow.h C++ header file, or C header file rather. And so we needed a way to port that into Java. And there was a question as to performance. I mean, there are a number of extremely quick Java programs, Hadoop, Tomcat, et cetera, but we weren't sure how it would perform. So Rob Sherwood and I, who will talk shortly, started working on a library called OpenFlowJ, which is an object-oriented bindings library for Java. And we built it initially just to try and find out performance and see what we got. This is a couple years old, but we were very happy with what we saw. Java looked competitive. It was certainly, these numbers, it was doing far less than a full-blown controller would do, but it looked like it was going fast enough that it'd be interesting to continue to build. So a couple other bullet points I wanted to hit on a new controller is I wanted it to be fully multi-threaded. I wanted the number of cores, I wanted the performance of the controller to increase based on the number of cores you have available in your system. At the time, there were no controllers that could do this that were publicly available. I also wanted to try out this runtime modularity thing that I just showed you. I wanted to use easy to understand abstractions, make it easy for the programmer, and use frameworks that were familiar to anyone that had done some development in Java. And also, as I showed you, a web UI was nice so that we could easily interrogate the controller at runtime. I also considered, instead of going from scratch, building on some existing software, I took a look at Tomcat. It had a lot of properties that seemed desirable. It had a really fast I/O engine, and it also had modularity in the form of wars, which are the unit of web deployment in Tomcat. But there was so much code there that it seemed not really a good use of time to try to figure out what was useful and throw away everything else. So I ended up going it on my own. So here's a picture of Intel's latest chip die, the Sandy Bridge processor. And I wondered what would happen if I tried to lay Beacon on top of that, what it would look like. And so Beacon is actually composed of a whole bunch of bundles. I'll talk much later in the talk about what bundles actually are, but they interact with each other. And I'm going to go ahead and talk first about what the core bundle does. So the core bundle's job is responsible for connecting directly to the switches, managing the byte to OpenFlow message conversion, and it's also responsible for enabling an interface for other bundles to receive packets through the controller. So it exports this service called iBeacon Provider, and applications come along and can use that to register and ask for particular OpenFlow message types. And this creates a linear pipeline through the system. You can see here an example of such a pipeline. Applications will register for the types they're interested in, and as packets come in from switches, they will be run through each application in sequence unless one terminates the pipeline. Beacon is fully multi-threaded in that it creates many threads when it starts up, generally one per CPU core, but this is configurable. And it binds switches as they connect to a particular thread. And all of those threads operate in parallel, pulling and decoding bytes into OpenFlow messages and running those through the applications. There's one instance of an application in Beacon, and it receives data from all threads. So you're responsible for any internal state synchronization that you need to do. So how do bundles interact? They have this service abstraction. You can see an example of a topology service here. And so this is just a Java service, and you export this to the service registry, and a bundle will create an implementation of this interface and push this out there, and so other bundles can come along and consume it. But they all interact through this interface that's been created for a service. So the underlying implementation can be swapped out, extended, whatever you want to do. Here's just another picture of what the service registry looks like. There's a number of interfaces there in the center. These bundles export implementations of the services, and other bundles can consume them. And this can happen dynamically. Services can come and go anytime during runtime. As you saw, we pulled hub out, we put learning switch in, and they both stopped consuming iBeacon provider and then started consuming it. So just a couple of examples of types of services. We have the simple queryable ones where it says, give me a list of everything that's connected or any other sort of state you're interested in. We have explicit event registration like the iBeacon provider provides, where you say, I want to receive all types of, all messages of this type, or notify me explicitly when switches connect or disconnect. There's also kind of an implicit event registration service where you state that you are interested in particular type of events and publish yourself, and then a service that can generate those events consumes everyone that's interested and then fires out to all of them. So we have lots of built-in bundles, kind of the typical stack that's available in most controllers today. OpenFlowJ does our protocol decoding in Java. We have typical packet header encoders and decoders, as well as learning switch, which I demonstrated, and hub. So some slightly more advanced modules are device manager, which tracks known devices across your network. Topology tracks links between OpenFlow switches and presents that to anyone interested. We have layer 2 shortest path routing, and then some more modules that I've used in my research to eliminate multicast. So we needed some proxies to do that, and then like the web UI. So those are the built-in bundles, but you can bring your own bundle to Beacon or create your own pretty easily. They're just a jar with metadata, and I'll talk more about that in just a second. So you may be asking yourself, is there actually a network information base in here? And the answer is there is not a centralized one in Beacon. It's decentralized. Relevant bundles store the state individually. So device manager tracks all of the devices, topology tracks all of topology, and you can interact with, and these guys generally export services so you can consume and interact with those that you're interested in. And Beacon right now, for simplicity, is soft state only. So nothing remains across controller restarts, but you can add persistence engines to extend this. So why bundles? Why all this talk of bundles? We have packages and classes and lots of other stuff in Java. So the bundle here is used primarily because it is the unit of modularity in OSGI, and OSGI is the framework that allows us to do this sort of runtime modularity. And like I said, it's the basic building block, and it contains metadata, some required metadata that exports what the bundle contains, what it needs from other bundles, and what version and stuff it is. So bundles are typical jar files. They can export code, import code, run code. Beacon is event-based and thread-based, so you can run threads, do whatever you'd like to do. And as you saw, these bundles are dynamic, and they can actually be versioned. So you can have multiple versions of a particular package running at once in Beacon if you'd like. So this is a sort of obligatory performance slide. This is getting pretty old in the tooth now. It's from last year. As Murphy mentioned, it may or may not be interesting to you depending on what your use case is. It's pretty much shown only to indicate that Beacon scales well per core and has pretty low I/O loop overhead. So if you're doing something performance critical, give it a try, see if it works for you. So what is the status of Beacon? So I started development on this in 2010, and we ran it internally and did a lot of testing with it for just over a year. It was released in a 1.0 version last September. The core is licensed under GPL with an exception that any bundles that you write around the core need to use an open source license of your choice. We have a list of those, BSD, Apache, those types of licenses. Development is still actively ongoing, and as all the controller developers have stated earlier, if you have features or bug reports, please let us know. We have an active user forum and screencasting guides available to get you started. Where is it actually in use? So, as I mentioned, I made this fundamentally for me to use for my research. So I have an active cluster courtesy of Google with 80 machines that are actively using it and 97 connected switches. It's inside Big Switch's controller and is the basis for Floodlight, which Rob will talk about shortly. We used it last year for a segment of the 244 graduate networking class at Stanford, and there are a number of other projects such as FlowScale currently using it. So sort of in conclusion here, what lessons have I learned from my time developing this controller? So I definitely improved my productivity. I feel like I spend, after I built the platform, I feel like I spend less time on the platform other than when developing it for new features. So that's been a win for me. I definitely learned that runtime dynamism and modularity has a cost. By introducing OSGI, it's another technology that you have to understand and be able to interact with, otherwise it can bite you. I spent a fair amount of time on performance in Beacon, and I found that like what you would expect to be minor changes can have a pretty large performance impact. Just running Beacon between 32 and 64-bit, you would think that you're running entirely different controllers because the 32-bit JVM is dramatically slower, which is surprising. We also use a library called Spring, and it turns out that between services, if you let Spring do its thing, you may have upwards of 30 function calls when you expect just one, and that can seriously degrade performance. Also, there's a wide variety of I/O loop designs, and those have a correspondingly wide variety of fairness and performance consequences. So carefully evaluate what you're doing there and make sure you understand what happens. So I left this slide in here from the tutorial. Please see me during that last session if you want to play around with Beacon. But there will be a number of archives for your platform. Just grab it, unzip it, do pretty much exactly what I did. And then if you want to do some coding, Google was nice enough to give me a shorter URL to the tutorial. And yes, that is an I in the end of that. I sucks. I don't know if they're trying to tell me something, but you can remember that, and it will get you to the tutorial instructions. So that's what I had. Thank you. I can take any questions if we have time. I'll let Rob talk about that next. Sure.
So throughput is one measurement of performance.
Yeah.
What happens to JIT when things like garbage collectors get going?
Definitely. So there are a number of good tools for Java to help you understand what your garbage collection use is. While running Rob's Cbench program here that generated those graphs, we saw garbage collection at less than 1% of CPU use. So it's definitely a function of how much memory you provide to the system, as well as how many objects you're throwing away quickly, what their size is, et cetera, what garbage collector algorithm is actually being run. If you provide Beacon with too little VM memory to work with, then it'll spend way more time trying to collect, and you can easily hurt yourself in performance there too.
But if your JVM memory space is large, then when garbage collector runs, it can be stuck running for a longer period. So what happens to the latency of new flow cell while that's happening?
Yeah, so it definitely depends on the algorithm. So there's a number of multi-threaded garbage collection algorithms as well as single-threaded blocking algorithms. I haven't done a good enough performance survey to state in general, but I haven't seen latency have a big impact on any of the existing benchmarks.
Are you measuring flow cell latency at all
We have those as well, yeah. I don't have a graph for that, but it's competitive with the other controllers.